welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 1836, remove duplicates from an unsorted linked list. In this problem, we're tasked with removing duplicate values from an unsorted linked list while preserving the original order of the remaining nodes. Let's dive into the solution and explore how we can efficiently solve this. In this problem, we're working with a singly linked list where each node contains an integer value. The goal is to remove all nodes that have duplicate values, leaving only the distinct numbers in the list. Importantly, the output list should maintain the original order of the remaining elements, but all duplicates must be removed completely. For instance, if a value appears more than once in the list, none of its occurrences should remain. The task is to return the head of this modified linked list. The input to the problem is the head of the linked list, and the output will also be the head of the resulting list after duplicates are removed. To illustrate, consider the example where the input list is 3, 4, 2, 3, 2. Here, the values 3 and 2 appear more than once, so they are completely removed from the list, leaving only the value 4. The output in this case would be 4. Now, let's look at another example to clarify the process. Suppose the input list is 1, 2, 3, 2, 1. In this case, the values 1 and 2 each appear twice in the list. Since duplicates are not allowed in the output, both of these values are removed entirely. This leaves only the value 3 in the list, which is distinct and does not have any duplicates. Therefore, the output for this example would be 3. Another example is when the input list is 1, 1, 1, 2, 3. Here, the value 1 appears 3 times. Since all occurrences of duplicates must be removed, the value 1 is eliminated completely. This leaves the values 2 and 3, which are distinct, resulting in the output 2, 3. Finally, let's examine the constraints and edge cases for the problem. The number of nodes in the linked list can range from 0 to 10⁻⁴, and each node's value can range from -10⁻⁵ to 10⁻⁵. This means we need a solution that works efficiently for very large lists. Additionally, the list is unsorted, so we cannot rely on the elements being in any specific order. For edge cases, if the input list is empty, the output should also be an empty list. Similarly, if all the nodes in the list have the same value, the output would be empty because all values are duplicates. On the other hand, if there are no duplicate values in the list, the original list should be returned unchanged. Lastly, the solution must handle negative values correctly, treating them just like positive values. These constraints and edge cases ensure that the solution is robust and handles all possible inputs effectively. To tackle the problem of removing duplicates from an unsorted linked list, we need to focus on eliminating all nodes with duplicate values while preserving the original order of distinct elements. Let's begin by exploring the brute force approach. The intuition here is to compare each node with every other node to identify duplicates. This involves using two nested loops. The outer loop iterates through each node, while the inner loop searches for duplicates. Once duplicates are found, they are deleted, and the list is rebuilt with only distinct nodes. The drawback of this approach is its inefficiency. It has a time complexity of n², making it impractical for large lists. However, it does have low space complexity, requiring 1 additional space. Despite its simplicity, this method quickly becomes infeasible as the size of the list grows, which is why we need to consider more efficient alternatives. Now, let's look at a more efficient strategy using a hash map for frequency counting. The intuition here is to count how often each value appears in the list. This can be done in two passes. In the first pass, we traverse the list and store the frequency of each value in a hash map. In the second pass, we traverse the list again, skipping over any nodes with values that appear more than once. This approach significantly improves time complexity to n, as we only traverse the list twice. However, it requires n additional space to store the frequency counts in the hash map. While this method is faster, it does have the drawback of increased memory usage. To address some of the challenges in list reconstruction and edge case handling, we can refine this further. That's where the optimized two-pass approach comes in. This approach introduces a dummy node to streamline edge case handling. We still use a hash map to count frequencies in the first pass. During the second pass, we used the dummy node to construct a new list containing only nodes with a frequency of 1. This simplifies the process of removing duplicates, particularly at the head of the list, while maintaining the same time and space complexity as the previous method. The chosen strategy for this problem is the optimized two-pass approach with a dummy node. It strikes a great balance between efficiency, clarity, and maintainability. By leveraging a hash map, we can efficiently identify duplicate values in constant time for each lookup. The dummy node ensures that we can rebuild the list without worrying about special cases, such as when duplicates appear at the very beginning. A key insight here is that preserving the original order of the list while removing duplicates requires a two-pass strategy. The first pass gathers frequency information, and the second pass reconstructs the list. The use of a dummy node eliminates the need for additional edge case handling, allowing us to focus on creating a clean and straightforward solution. This approach elegantly combines the efficiency of the hash map with the simplicity of robust list manipulation, making it an ideal choice for this problem. When comparing the different approaches, the trade-offs become clearer. The brute force method, while simple to understand, is highly inefficient with its n² time complexity, making it unsuitable for larger lists. The hash map with frequency counting improves the time complexity to n, but it requires n additional space. This trade-off is often acceptable for the performance gains it provides. Finally, the optimized two-pass approach combines the time efficiency of the hash map with the robustness provided by the dummy node, making it the most balanced solution. By adopting this approach, we ensure both clarity in implementation and optimal performance. This makes it the preferred strategy for solving LeetCode problem number 1836, effectively addressing both the functional and efficiency requirements of the problem. In problem number 1836, remove duplicates from an unsorted linked list. The task is to remove all nodes with duplicate values while preserving the relative order of the remaining distinct elements. The challenge is that the list is unsorted, so we can't rely on sorting to identify duplicates. To address this efficiently, we use a hash table for frequency counting. First, we initialize an empty hash table to track the frequency of each value in the linked list. Hash tables are ideal here because they provide one average time complexity for both insertion and lookup. Next, we traverse the linked list starting from the head. As we visit each node, we increment the frequency of its value in the hash table. By the end of this pass, the hash table will contain the frequency of every value in the list, giving us a clear picture of which values are duplicates. Once we have the frequency counts, the next step is to remove the duplicates. To simplify edge case handling, we create a dummy node that points to the head of the linked list. This dummy node acts as a placeholder, ensuring that operations on the head node are consistent with the rest of the list. We then traverse the linked list again using two pointers, previous to track the last non-duplicate node and current to process each node. For each node, we check its frequency in the hash table. If the frequency is 1, it means the value is unique, so we link previous to the current node and move previous forward. If the frequency is greater than 1, the value is a duplicate, so we skip the node by adjusting previous.next to bypass current. This process continues until the end of the list. If the list contains only duplicates, the dummy node remains unchanged. If there are no duplicates, the list structure is preserved. Finally, we return dummy.next as the head of the modified list. This approach hinges on a few key insights. First, the efficiency of the hash table is crucial. It allows us to count frequencies in n time, making this method far more efficient than a brute force approach using nested loops. Second, the use of a dummy node greatly simplifies edge case handling, such as when the head node itself is a duplicate. Third, the two-pass structure of the algorithm separates the frequency computation from the deletion logic. This separation makes the implementation both cleaner and easier to debug. In terms of data structures, we rely on a hash table to store frequency counts, which provides constant time operations on average, and two pointers, previous and current, to traverse and modify the linked list. Together, these elements form a robust and efficient solution to the problem. Analyzing the complexity of this algorithm, the time complexity is n. The first pass, which involves counting frequencies, takes n, where n is the number of nodes in the list. The second pass, which removes duplicates, also takes n. Combining these, the total time complexity remains O(n). The space complexity is also O(n) due to the hash table, which may store up to n unique values in the worst case. To understand this better, consider an example. Suppose the input linked list is 4-5-6-4-7-5. During the first pass, we build a hash table to store the frequencies of each value. After this pass, the hash table looks like this: 4 appears twice, so its count is 2, 5 also appears twice, so its count is 2, 6 and 7 each appear once, so their counts are 1. With this frequency data, we can confidently identify which nodes need to be removed. Now, let's process the list to remove duplicates based on the frequency data. Starting with a dummy node pointing to the head, we traverse the list and evaluate each node's value. The first node has the value 4, which appears twice in the hash table, so we skip it. The next node has the value 5, which also appears twice, so we skip it as well. The third node has the value 6, which appears only once, so we keep it. Similarly, the fourth node has the value 7, which also appears only once, so we keep it. At the end of this traversal, the modified linked list contains only the unique values, 6-7. This process ensures that all duplicates are removed while preserving the relative order of the distinct elements. Let's also review some edge cases for clarity. For edge cases, consider an empty list as input. In this case, the output is also an empty list since there are no nodes to process. If the list contains only duplicates, such as 1-1-1, the output will be an empty list because all nodes are removed. On the other hand, if the list has no duplicates, like 1-2-3, the output remains unchanged as 1-2-3. Finally, for a single element list, such as 1, the output is the same single node since there are no duplicates. These cases confirm that the algorithm handles all scenarios robustly, ensuring correctness across a wide range of inputs. Here, we start by defining a method within the solution class called DeleteDuplicates_Unsorted, which takes the head of the linked list as input. The very first thing we do is check if the head is none. If the list is empty, we simply return none because there's nothing to process. Next, we need to count the frequency of each value in the linked list. To do this, we initialize an empty dictionary called frequency. We then traverse the entire linked list using a while loop, where the current node is iterated one by one. For each node, we extract its value and update the frequency in the dictionary. If the value already exists in the dictionary, we increment its count, otherwise, we set it to 1. This gives us a complete frequency map of all values in the linked list. After counting the frequencies, we create a dummy node with a value of 0. This dummy node helps simplify the manipulation of the list, especially when removing elements. We set its next pointer to the head of the list. We also initialize two pointers, previous, starting at the dummy node, and current, starting at the head. These pointers will help us traverse and modify the list as needed. Now, we begin removing nodes that have duplicate values. Using another while loop, we iterate through the list. For each node, we check its value in the frequency dictionary. If the frequency is greater than 1, that means it's a duplicate, so we skip the node by adjusting the next pointer of the previous node. Otherwise, we simply move the previous pointer forward to the current node. In either case, we advance the current pointer to continue processing the list. Finally, after we've processed all the nodes in the list, we return dummy.next. This ensures that the result starts from the head of the modified list, skipping the dummy node. By this point, all nodes with duplicate values have been removed, and the original structure of the linked list has been preserved for the nodes that remain. This approach is efficient because we only traverse the list twice, first to count the frequencies and second to remove duplicates. The use of a dummy node makes it easier to handle edge cases, such as when the head itself needs to be removed. This completes the solution. Here, we start by defining the basic structure of a singly linked list using a class called ListNode. Each node contains an integer value and a reference to the next node. The constructors allow us to create nodes with or without specific values or next references. Then, we define the main solution method, DeleteDuplicates_Unsorted, which takes the head of the linked list as input. The first step in solving this problem is to handle the edge case where the list is empty. If the head is null, we simply return null. Next, we create a hash map to store the frequency of each value in the list. We iterate through the linked list using a pointer called current. For every node, we update the frequency map by incrementing the count for the current node's value. This gives us a complete picture of how many times each value appears in the list. After building the frequency map, we simplify our operations by using a dummy node. This dummy node acts as a placeholder before the head of the list, making it easier to handle edge cases like removing the head node. The dummy node's next pointer is set to the head of the original list. We then use two pointers, previous and current, to traverse the list. The while loop iterates through each node, and for nodes with values that appear more than once in the frequency map, we skip them by adjusting the next pointer of the previous node to bypass the current node. If the value is unique, we simply move the previous pointer forward to the current node. Regardless of whether the node is skipped or retained, the current pointer is moved to the next node in the list. Finally, after processing all nodes, we return dummy.next, which points to the head of the modified list with duplicates removed. In this example, we start with an input linked list of 3, 4, 3, 2, 6, 2. The goal is to remove all nodes with duplicate values. The first step is to count the frequency of each value in the list. We use a dictionary to store these frequencies as we traverse the list. Initially, the dictionary is empty. When we encounter the first node with the value 3, we add it to the dictionary with a count of 1. Next, we process the node with the value 4 and add it to the dictionary. When we encounter another 3, the count for 3 is increment to 2. We continue this process for the remaining nodes, updating the dictionary accordingly. By the end of the traversal, the frequency dictionary is 3, 2, 4, 1, 2, 2, 6, 1, which tells us which values are duplicates and which are unique. Now that we have the frequency of each value, we can remove the duplicates. To make this process easier, we introduce a dummy node that points to the head of the list. We use two pointers, previous, which starts at the dummy node, and current, which starts at the head. As we traverse the list, we check the frequency of the current node's value. If the frequency is greater than 1, we remove the node by updating previous.next to skip current and point to current.next. For instance, the first node with value 3 has a frequency of 2, so it is removed. The next node with value 4 has a frequency of 1, so we keep it and move previous to this node. This process continues for all nodes until we reach the end of the list. After removing all duplicates, we are left with the final list, 4, 6. In this example, the input linked list is 1, 2, 3, 4, 5, and there are no duplicates. As before, the first step is to count the frequency of each value. We initialize an empty dictionary and traverse the list. Each value is encountered exactly once, so the frequency dictionary becomes 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. Since all frequencies are 1, there are no duplicates to remove. When we traverse the list to remove duplicates, we find that all nodes have a frequency of 1, so no nodes are removed, and previous simply moves along the list. The final output remains the same as the input, 1, 2, 3, 4, 5. Here, the input linked list is 7, 7, 7, 7, where all nodes contain the same value. We start by counting the frequencies. As we traverse the list, we update the frequency dictionary. The first node with value 7 is added with a count of 1. Each subsequent node increments the count for 7, resulting in a final frequency dictionary of 7, 4. Since all nodes have a frequency greater than 1, all are considered duplicates. During the removal step, we traverse the list and remove every node because their frequency exceeds 1. By the end of this process, all nodes are removed, leaving us with an empty list. The final output is therefore an empty list. To understand the time complexity of our solution, let's break it into 3 main steps. First, we traverse the linked list to count the frequency of each value. Since we visit each node exactly once, this step takes n time for a list with n nodes. Next, we make another pass through the list to remove nodes with duplicate values. Again, because we're visiting each node only once, this step also requires n time. Lastly, we perform operations on the frequency dictionary, such as retrieving and updating its values. These operations are O1 on average, thanks to the hash table implementation of Python dictionaries. Since these operations are performed n times, their total contribution to the time complexity is O(n). Adding up these three components, the total time complexity of the solution is O(n) plus O(n) plus O(n), which simplifies to O(n). Now, let's analyze the space complexity. The frequency dictionary stores entries for each unique value in the linked list. In the best case, where all values are unique, the dictionary will have n entries, resulting in O(n) space. Additionally, we use a dummy node and two pointers, which together require O(1) space. Combining these, the overall space complexity is O(n) plus O(1), which simplifies to O(n). When comparing this optimized approach to a brute force method, the difference becomes clear. A naive solution would involve nested loops, where for each node, we check all other nodes for duplicates. This would result in O(n) squared time complexity due to repeated traversals, though it would only use O(1) space since no extra data structures are involved. In contrast, our optimized solution reduces the time complexity to O(n) by using a frequency dictionary. While this adds an O(n) space requirement, it eliminates the inefficiency of nested loops, making it far more scalable for larger lists. Now, let's consider the best, average, and worst case scenarios. In the best case, where all values in the linked list are unique, we only need a single traversal, resulting in O(n) time an O(n) space for the dictionary. In the average case, where some but not all values are duplicates, the time complexity remains O(n), while the space complexity depends on the number of unique values, OU. Finally, in the worst case, where all values are duplicates, the time complexity is still O(n), since we traverse the list once, but the space complexity drops to O(1), because the dictionary only contains one key. The linear time complexity arises because we perform a constant number of operations per node, and the space complexity depends solely on the number of unique values, which in the worst case is minimal. One common mistake in this problem is not accounting for edge cases. For example, if the linked list is empty or contains just one node, attempting to perform operations without checks can lead to issues like null pointer exceptions. To address this, always verify if the head is null or if the list has only one node before proceeding with your main logic. Another issue arises when modifying the list while iterating. If you remove nodes directly without updating pointers correctly, you could accidentally break links or skip nodes. A safer approach is to use a two-pass method or introduce a dummy node that simplifies pointer management. Additionally, space usage can become inefficient if you store the entire list in an array or use redundant data structures, which can lead to a space complexity of O(n) squared. To avoid this, leverage a hash set or dictionary for efficient duplicate tracking. Finally, it's important to preserve the original order of the list. Mismanaging this can lead to reordered nodes or outputs that don't meet the problem constraints. To ensure this, process nodes sequentially and only remove duplicates while maintaining their relative positions. Inefficient duplicate detection is another pitfall to watch out for. Using nested loops or redundant checks increases time complexity to O(n) squared, which becomes impractical for large linked lists. A better solution involves using a hash map to count occurrences in the first pass and removing duplicates in the second pass, optimizing the process. Now, during interviews, you may be asked to compare the hash map approach with a two-pointer method. A hash map is simpler and achieves O(n) time with O(n) space but may lead to follow-up questions regarding space optimization. In contrast, the two-pointer approach uses O(1) space and is more efficient in terms of memory, though it can be challenging to implement correctly. Interviewers also value your ability to identify and handle edge cases, such as lists with all unique values, all duplicates, or a mix. This shows thorough debugging skills. Finally, always aim for optimal complexity. For this problem, O(n) time is achievable, and you should choose between O(n) or O(1) space depending on the constraints. Be ready to justify how your solution meets these requirements. To deepen your understanding of linked lists, it's helpful to practice related problems that build on similar concepts. For instance, LeetCode 82 focuses on removing duplicates from sorted lists, specifically targeting cases where duplicates should be entirely eliminated. LeetCode 83 presents a simpler variation, where you remove duplicates but only deal with a sorted list. This helps reinforce your knowledge of sequential node processing. Another useful problem is LeetCode 142, which involves detecting cycles in a linked list using techniques like hash sets or two pointers. This expands your understanding of pointer manipulation and memory trade-offs. Finally, LeetCode 160 challenges you to find the intersection of two linked lists. Here, the focus shifts to identifying common nodes, which can be addressed using shared techniques like hash maps or optimized pointer traversal. These problems collectively strengthen your grasp of linked list manipulation and help you approach a variety of scenarios with confidence. There are several approaches to solving this problem, each with its own trade-offs. The recommended method is the two-pass approach with a hash map. First, traverse the list to count occurrences of each value using the hash map. Then, in the second pass, remove duplicates by referencing the map. This method is easy to implement, achieving O(n) time complexity with O(n) space. For environments where space is limited, the in-place removal technique is a better option. This approach uses two pointers, one to traverse the list and another to keep track of the last distinct node. Duplicates are removed as you go, achieving O(1) space while maintaining O(n) time. However, this method is more complex to implement and requires careful pointer management. Lastly, there's the brute force approach, where you use nested loops to compare each node with all subsequent ones, removing duplicates along the way. While this method is straightforward, it has an O(n)² time complexity, making it unsuitable for large inputs. Understanding these trade-offs helps you choose the best solution based on the problem's constraints and requirements. Great job following along. To wrap up, we learned how to use a hash map to remove duplicates from an unsorted linked list while maintaining the order of unique elements. This solution demonstrates the power of hash maps for efficient duplicate detection and reinforces key concepts of linked list manipulation. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!